Welcome to our webinar on testing at non-ambient temperatures. Thank you so much for being here. I'm Nick Erickson, your host for this webinar. Before I introduce our presenter, I was hoping to ask our audience just a couple quick questions to get an idea of who's with us and what sort of materials you're working with. So I'm going to put up a poll question real quick, if you don't mind responding. So this one is very simple. Do you test any materials at non-ambient temperatures? Yes or no? All right, so results are coming in. Yeah, look, pretty typical. This webinar is about temperature testing, so as expected, there's a fair amount of you that are testing at temperature. I'm just gonna share those results. So yeah, about 78%, yes, you are testing at non-ambient temperatures. And I do also have one other question that I'm just gonna throw up real quick. Let's see here. Just gonna launch that second poll. So what types of materials do you test at non-ambient temperatures? This one, I set it so you can select multiple. That just makes sense if that's applicable. So we'll give you a second just to respond to that. All right, so I'm gonna close out that poll and then I'll share the results here. So pretty even spread, a lot of metals and plastics, elastomers, composites, so a fair amount. So yeah, I'm gonna close that out here. Thank you for responding to that. So now that I have a general idea of who's joined us today, I wanna introduce our presenter, Stephan Botzki. I think he'll pop on here in a second. There he is. Stephan is an application engineer at Instron that works on a lot of our high force application projects. So he sees a lot of metals and composite applications that get tested on some of our larger universal testing systems. That being said, this webinar isn't specific to just that material type or higher force applications. It's definitely going to be broader in scope than that. We're also joined by Ian McIntaggart, another member of our high force applications team. Ian has hosted a few of our other recent webinars about composites and alignment, and has worked with Instron for over 45 years. He's a true wealth of knowledge, and we're very fortunate to have him here to keep an eye on questions while Stephan is presenting. So I encourage you to submit any relevant questions you might have here as we go along, some of which Ian may address directly via chat while Stephan is presenting, and others we'll address at the end. And we already received a lot of great questions in advance, so you want to make sure you hang out after the presentation to hear us address those. So with that said, I'm going to turn things over to Stephan.
Yeah, thank you, Nick. And hello, everyone. Thank you so much for joining us today for our webinar on testing at non-ambient temperatures. Here are the topics that I would like to touch on today. First, we will talk about why it is so important to test materials at non-ambient temperatures. After that, we will look at how an environmental chamber works and focus on some important things to consider when testing with an environmental chamber. Once that's out of the way, I'll show you the best options to measure the strain in the chamber, followed by solutions on how to grip specimens. Lastly, I'll show you mounting options for our chambers before we jump into the Q&A. Okay, just to clarify for you, in case you haven't seen one yet, this is what we'll be talking about today. Here you can see two different test frames. One is a floor model here on this site, and the other one is a table model. Both of these frames are equipped with an environmental chamber between the test frame columns, as you can see here. And the test will be performed within this chamber, and the operating ranges of these are between minus 150 degrees C up to 600 degrees C. So why is it so important to test your materials at very hot or even freezing temperatures? The reason is that materials behave differently when exposed to temperature changes. If we take a car manufacturer, for example, they won't design the same type of car for different environments. Instead, they will conduct tests to ensure that the materials they're using function without failure in all environments. You wouldn't, for example, you wouldn't want your dashboard to melt just because you parked your car in a hot environment, or your windshield to crack when you're in a freezing environment. To give you a more recent example, some of the COVID-19 vaccinations must be stored at very low temperatures. So all of the related components need to be tested for function at such low temperatures as well. And maybe also another example, if you think about an airplane, they go through very different temperatures and other conditions if you compare it on the ground to in the air, and then maybe even the places in between where you're flying. And you got to ensure that all of the materials function without failure in all the different environments. The problem for designers is that materials can change from ductile to brittle or vice versa when exposed to a temperature change. So how does this then translate into a stress strain plot when testing different materials? As you can see here on this plot, ductile specimen has much more significant reduction in diameter before failure compared to the brittle specimen, which absorbed very little energy before its failure. You can also see this when you're looking at the actual specimens after the test. Ductile specimens can sustain elastic and plastic deformation under load and clearly deform before failure. When we compare this to the brittle specimen, there's very little reduction in diameter before failure, and both ends of the test specimen are much flatter. This is an Ashby plot with many different materials and their maximum strength versus service temperature. So here you get the strength increasing exponentially, and on the bottom we got the service temperature increasing. Each material is shown in a range because it depends on how the material was produced. If we take stainless steel up here, for example, it will have a different maximum strength and service temperature depending on the alloys and the way that it was produced. On the left and on the right side, you can see some examples for ductile or brittle products. As an example for ductile products, you can think of the tires on your car, for example, as a brittle product. You can think of the cause on your tire, and for a brittle product, you can think about a cast iron pan in your kitchen, maybe. And then highlighted here in blue, you can see the temperature range that we're covering, the materials that we're covering with the temperature range that we're talking about today. Now let's look at how a chamber actually works. And you might be surprised, the way a chamber works is not that much different from your oven that you have at home. We're using the forced convection principle to heat up or cool down our environmental chambers. It all starts at the top of the chamber. Here you can see where the air is drawn in and forced over heating elements with the help of impellers. We have the first impeller here for venting the space between the inside and outside of the chamber, which you can see here highlighted in blue. This prevents the outer wall of your chamber from getting too hot or too cold during a test, depending on what type of test you're running. The other impeller is distributing the hot or cold air inside of your chamber to bring your specimen and load string to the desired test temperature. Now let's look at some things that need to be considered with an environmental chamber. The first few things to consider are, what type of test do I actually have to perform, and how much space and travel do I need for that? As a test solution provider, we ensure that there's enough test space for our customers' applications with the help of various tools and even integration drawings. As you can see here on the slide, we need to determine the correct pull rod lengths for this customer's application. We will select the right pull rods and piggybacking options for an optimal use of your test space inside of your chamber. In this case, you can do high strength tensile testing with the grips when you roll the chamber out of the test space. And if you want to do your tensile testing at temperature, which you would do at lower forces, you can roll the chamber back into the space, and then with the help of the small pneumatic grips piggybacked on pull rods, you can run this test. So this gives you lots of flexibility on your test frame. This is another program we're using to check the load string inside your chambers when we're configuring a test system for our customers. There are different gripping and chamber options that you can choose from, and this is a very quick and easy way for us to check how much travel will be available within of your testing chamber. Okay, now let's clarify what pull rods actually are. In a nutshell, these are basically extensions for your grips that lead into the chamber. As you can imagine, you need to somehow get the grips into the chamber, but you also want to have the openings as little as possible to ensure temperature uniformity within your chamber. You wouldn't want any of your hot or cold air that you're blowing into the chamber to escape during a test. So with the help of round pull rods and then the corresponding port plugs and insulation material, we can ensure a shielded environment inside of our chambers without much of the air escaping. The next thing that you need to consider is the alignment of your load string. As you can see here in this example, a little misalignment at the beginning of your pull rod can go a long way all the way to the bottom. And depending on the length of your pull rod, it gets worse. The other issue that you could be facing is misaligned concentricity. So there are alignment fixtures available, which are mounted between the crosshead and the load cell. And these will help, and with the help of alignment software and the strain gauge specimen, these alignment fixtures can minimize the bending in your load string to help you get the highest results possible during a test. My colleague Ian McIntyre, who also joined us here today, held a webinar on this topic a few months ago, and Nick will drop a link into the chat for you, which you can follow to watch a recording of that session. I really highly recommend it. So this is how this alignment fixture would look like if it's installed on your test frame. And you can see here the big crosshead, and then here your big 250 kilonewton load cell in this case. And then this is the alignment fixture. It can be installed, and then you have some screws here on the side that you can use for adjustment. And yeah, this is how you can perfectly align your load string. Another important thing to consider is the capacity of your test frame. Let's walk through a few examples here. If you're always testing at non-ambient temperature and you expect relatively low forces, then one of our LFA frames equipped with a chamber might be all that you need. However, if you're testing specimens at ambient with high forces, but also want to conduct temperature testing where you expect much lower forces, then one of our floor models is the right solution for you. You can roll the chamber in and out of the test space, and piggybacking smaller grips with the help pull rods to test inside of your chamber. So this gives you a lot of flexibility, like we saw in the previous example. The last example is for anyone who always needs to test specimens with high strength at non-ambient temperature. The best solution for this scenario would be a floor model equipped with extended hydraulic or precision manual wedge grips. And you can see here one with the extended hydraulic wedge grips, and then here with compression platens in case that you're interested in compression testing. I mentioned piggybacking a few times, so I added this slide with a few different drawings to illustrate what we mean when we're talking about piggybacking. We have the same test frame. Equipped with different fixtures in between the precision manual wedge grips, as you can see here in the middle. The compression platens mount directly on top of the grips, and the different fixtures can be placed in between for the testing. This gives you a lot of flexibility without having to remove any heavy grips or other accessories. As you can imagine, that might be quite the process. An important factor in being able to piggyback smaller grips and fixtures on a large capacity test frame is the resolution of your load cell. Our load cells can measure down to 1/1000th of their capacity to an accuracy of 0.5% of the reading. As an example, if you have a large 250 kilonewton test frame for high strength tensile testing, and you also need to perform a flex test, which usually requires lower forces, you can still measure the forces during that flex test down to 250 newtons. And if that's not low enough, you can simply piggyback a smaller load cell below your main 250 kilonewton load cell if you need to. To be able to test at sub-freezing temperatures, you will need either liquid nitrogen or carbon dioxide. As we have seen on the slides about how the chamber actually works, you would run either option into your chamber with the help of the impellers to cool down your load string. Now, depending on your load string, this could require a substantial amount of LN2 or CO2 before you reach the desired test temperature. So you really need to ask yourself, how often do I need to test at freezing temperatures, and how much gas would that actually require? And no matter if you're testing at high or low temperatures, soaking time is really something that will matter to you. And an important thing to consider is the thermal mass of your load string components, because they can really heavily influence the soaking period. We have features in our Blue Hill Universal testing software that let you define a set point at which the test will automatically start. This can save you time and energy. Here's an example of how it looks in our software. As you can see here highlighted, we're in the test control tab and then in the pre-test menu. And this is where you can set a soaking time or a temperature set point. The soaking time is usually the longest part of your test sequence, and there are some things that can help you to reduce it to a minimum. One good example would be to simultaneously soak multiple specimens at the same time. You could measure the batch of your test specimens, load the first one into the grips, and lay the other ones on the bottom of your test chamber before you close the door. In general, it is a good idea to keep the chamber door closed as much as possible. Using pneumatic grips and contactless strain measurement will help you with that. If you require a very high level of throughput, you should consider a test frame with multiple load strains. You can see here in the picture. And these frames can also be equipped with environmental chambers, which will allow you to run multiple tests at once at temperature. So if you're looking for really high throughput, this could be really an option for you. Okay, now let's look at some different options to measure the strain during a temperature test. The first option we will look at are strain gauges. As you can see in this picture here on the top, they're directly bonded to the test specimen. The operating range of these depends on the manufacturer and on the bonding material, which can become a challenge. Depending on the strain gauge, these might also have to be temperature compensated. The next option would be clip-on extensometers, which also come in a wide operating range. You would usually attach these when you set up your load string before you close the chamber door for the soaking period. Since these are directly attached to your test specimen, you must take the behavior of a test specimen at temperature into account. You would also not want to remove these prior to failure unless you really have to, because that would require you to open the chamber door, and as you can imagine, this will greatly affect your test temperature. This brings us to the last and preferred option, which is contactless strain measurement with our advanced video extensometer. This is the best solution for strain measurement at temperature, and since it's contactless, you won't have to open the chamber door, which will keep your temperature very, very stable. It also makes the setup very easy and operator friendly. The low end of the operating range can vary and depends on your lab environment and humidity. The glass of our chamber doors is heated to prevent freezing at low temperatures to allow the AVE to look through the glass. Customers also sometimes approach us about automatic contacting extensometers that can be used in a chamber. However, this is not an advisable solution for testing at temperature because, for once, the floating air within the chamber can affect your strain map. And in addition to that, the opening that would be needed in the back of the chamber for the extensometer arms to reach in will affect temperature uniformity inside of your test chamber during the test. Therefore, we recommend contactless strain measurement as a preferred option if you're testing at temperature and you want to measure the strain of your specimens. Next, I will show you different options to grip your specimen during a test inside of a chamber. On this graph, we plotted 3 different types of grips against their cost and their effectiveness. The mechanical wedge grips are a great low-cost solution with a wide operating range in terms of temperature and force. And if you're looking for a more automated solution for lower force test, pneumatic side action grips are really the best way to go for you. In the very high force range, hydraulic wedge grips will give you the most flexibility. As we mentioned before, you can piggyback compression platens and other test fixtures on them. And if you're ever experiencing jaw breaks, you can adjust the clamping pressure of these to try to minimize those. Okay, the last topic for today is how you can actually mount a chamber onto your test frame. By far the most popular way of mounting a test chamber is a roller mount, which you can see in this picture on the left side. This allows you to roll the chamber in and out of your test space And another custom solution that we have designed is a removable roller mount on a trolley, as a removable mount on a trolley. This allows you to move the same chamber in between two different test frames. And now I want to show you a video that I prepared to demonstrate one of our roller mounts. Okay, so this is one of our test frames. It's a low force table model equipped with the chamber, as you can see here. So first thing, if you want to roll this out of the test space, you open the door and then you take out the two port plugs on the top and on the bottom, because you have two pull rods come in of your test space. And then you got to make sure that you have enough clearance and take out the two screws in the front, which secure your chamber at the right position. And then you make sure that you have enough clearance and you can simply push the chamber to the back outside of your test space. And now you could do normal ambient testing. As you can see, it's really easy. You can do this with one hand, and then if you need to, you just for the temperature testing, you can just simply pull back the chamber again, pull it in position, and then you start putting back in the securing screws in the front, and you put back in the port plugs, close the door, and you're ready to test the temperature again. So it's a very easy way. It's probably the best solution for most people, and yeah, it's very easy and gives you lots of flexibility, and you can do both types of testing on one frame. So we just put the port plugs back in, and we're ready to go again to test the temperature. Okay, I got one more video where I demonstrated how to put the AVE from the frame column onto the test chamber. Okay, you can see here the front of our chamber, and this is our part with the hinges on. This is what we're gonna put the AVE onto, and you can see on the left side here, we undo those two screws, one on the bottom and the one on the top, and this lets us lift the AVE off of the hinges, and then we can place it right on top of the chamber door, and you're basically ready to test with the AVE inside of your chamber and measure the strain. So this is a nice option. Again, gives you much flexibility, and yeah, for your non-ambient and for your ambient testing, you can use the same device and just flip it over. Okay, now with all that being said, let's look at a little summary of tips for testing at non-ambient temperature. And the first tip I have for you is heating up your chamber after a cold test to clear out all of the moisture that accumulated during the test. As you can see here in this picture, the grips really freeze up from the humidity in the air around them during a test inside of a chamber. And if you can imagine, if you now just let the chamber go back to ambient temperature, there will be a lot of moisture inside of the chamber that will collect on the bottom. And yeah, it's a really good idea to then heat up your chamber to clear out all of that moisture afterwards, after your cold tests. Now, the next tip is kind of the other way around. If you're running a test at very low temperatures, you can heat up your test chamber to clear out all as much moisture as possible before the test. The next tip is, as I mentioned earlier, we recommend a video extensometer for strain measurement because it's best to keep the temperature stable and is most operator friendly for you. And then we got a little summary here of the most important tips, most important things that you need to consider with a non-ambient test setup. For example, is alignment important to you? Or do you need to piggyback? Are there many different test types that you need to run? And is piggybacking maybe a solution for you that lets you do that with only one frame or as little frames as possible? The next thing would be, if you're running lots of tests at freezing temperatures, how much LN2 and CO2 do I actually need for all of those tests? And then again, no matter if you're running cold or hot tests, you need to consider the soaking time that it takes every time for your load string to get onto the right temperature. And lastly, if you're already using our Boolean Universal Testing software, make sure to make use of the automated options with specific temperature set points or the soaking time, as I showed you earlier. So I hope these tips are useful for you when you have to test that temperature. And with that, I'd like to turn it over to my colleague Ian McIntyre for the Q&A.
Okay, thanks very much, Stephan. Hello, everyone. Okay, so we have a list of questions that were submitted along with the registrations, and we'll go through those. At the same time, if there are other questions that come to mind, please fire those questions in and we'll try and answer those as best we can. Okay, so first question, I'm interested in best practices for controlling temperatures below ambient and above liquid nitrogen temperatures. Well, we would, the chambers that Stephan has been talking about are very suitable for this. The cooling technology, as mentioned, is basically using liquid nitrogen or CO2 cryogens. They are introduced into the chamber with a valve, and there's a closed loop control system closed around a thermocouple in the air temperature, in the air stream, and that is a very effective way of cooling, because these cryogens are very efficient. They're very high thermal mass, and very effective way of cooling down to those temperatures. So we would say that those are the best practices. Closed loop control of a cryogenic liquid. There are other ways to cool. I mean, there is mechanical refrigeration using basically similar approach to the approach you'd have in a domestic refrigerator. But the cooling power of the mechanical cooling system is not as great as the cryogens. They don't cool down as quickly, and it's difficult to get temperatures below round about minus 40, minus 70 degrees centigrade with that technology. So that's that. How does thermal shock affect materials in general? I have to say, thermal shock is not something that Instron has a great deal of experience of. We know there are chambers that are designed to look at thermal shock effects, mainly, I believe, in electronic sub-assemblies. And these chambers basically have a hot zone and a cold zone, and the assemblies under test are moved between the two areas. That creates a thermal shock. So but that's again testing electronic assemblies rather than materials themselves. Then we have a couple of related questions. Common stabilization times for manually exchanging test specimens when an automatic system is not available, and recommended stabilization time for starting a test when you're working at temperature. Well, I mean, I think it's worth saying that there are really two stabilization times generally. There's the stabilization time for the chamber and the associated accessories, where you would, for the initial cool down or initial heat up, so initial getting to the set point, and at that stage, you would have a stable air temperature, you would have a stable, your grips and other accessories would be at a stable temperature. And then there is the stabilization time when you actually put the specimen into that environment, and then the specimen comes to a stability. Now the stabilization times for the chamber and the accessories can, depends hugely on the size of the chamber, the mass of the grips. Stephan was showing us some very large hydraulic grips in large chambers. If you were going down to minus 70 centigrade with a chamber like that, it may well take several hours to actually stabilize at temperature. On the other hand, when you change the specimen, that stabilization time is probably of the order of 20 to 30 minutes, and typically that's kind of the time. So that's the time that for the specimen to come to equilibrium with the environment. So there's the associated question here: could the cell be affected? So I believe we're talking about the load cell here. Now, again, in the configurations that we've been talking about today, and generally, the load cell is located outside of the chamber. So, the load cell is not directly in the environment. It's not subject to the heat or the cold. There will be some conducted heat or cold into the load cell, and that's why all of Instron's load cells are actually temperature compensated over the range of up to 50 degrees C. And then when we actually check the temperature compensation on every single load cell that we make, we put them into a heated chamber and check them that they are not affected by that kind of temperature. So that is the answer there. Use of DIC and IR, I assume infrared, if possible, sensors. Yes, Stephan showed us the video extensometer. The video extensometer does actually have a DIC capability. So the camera can look through the window of the chamber. We can use it in DIC mode inside the chamber. That's a 2D single camera DIC system. Looking at multiple, say, 2-camera 3D DIC systems, they would generally require a larger window. And it is possible to supply the kind of chambers we've been talking about today with larger windows, which allow both cameras to see the specimen and also to get illumination into the chamber. The chambers do have an internal light, which allows observation of the specimen. But if you're using high-speed DIC, or you might need more illumination, so you're going to have a light source outside of the chamber. Infrared. I'm not aware of. I mean, infrared sometimes used for temperature measurement. The window materials are not particularly transparent to infrared, so infrared is probably would be a problem, I think, without having special window materials, and so not really able to comment on that too authoritatively. Pre-soak capabilities within Blue Hill Universal Software. Again, I think Stephan's covered this. Blue Hill Universal Software has the ability to set a set point for temperature set point and set a soak time. So set a set point, start things running, the chamber will heat up, and then after a predefined soak period, the test can start automatically. So does temperature affect yield point determination methods, or which are the best yield point determination methods to use at temperature? Essentially, I think the methods would be the same methods that you would use at room temperature, but there are going to be some potential changes. I think obviously to determine a yield point, we require measurement of an elastic modulus, and as temperature increases, the actual elastic limit will probably reduce. So the linear portion of the elastic part of the curve is going to reduce in size, and that's going to make determination of the modulus a little bit more challenging. Obviously, the smaller area you have to fit on the curve, the less accurate your modulus is going to tend to be. Again, Blue Hill software has several different methods of modulus determination, so it should be possible to find an optimum modulus determination method even in these challenging situations. Okay, next question. Can these chambers also provide controlled relative humidity environment? We do not manufacture chambers that provide controlled relative humidity. It is possible to have chambers with controlled relative humidity, and we have integrated chambers from third-party suppliers, specialist suppliers of humidity chambers, onto our equipment. That can be quite a challenging thing to do. It's certainly at high levels of humidity, it's necessary to implement things like heated grips and heated pull rods in order to prevent, because if you have anything that is colder than the chamber environment, you will instantly get condensation onto those cooler parts. So you have to have everything at the same humidity, same temperature, in order to prevent that condensation. Another comment here is that composite materials are routinely conditioned in humid environments, but that conditioning will take several days, several weeks for these materials to come into equilibrium with that humidity, and then the testing, which takes minutes or several minutes, can be done in a standard temperature environment. There's no need to maintain the humidity because the materials will not lose the absorbed moisture in the time taken to do the test. So low temperature and cryogenic testing, I think we talked about the ability of the chambers, and going down to minus 150 with the liquid nitrogen cooling. Below these temperatures, the solutions would be possibly actually testing in a liquid nitrogen bath, so literally in a bath of liquid nitrogen. This is not something we supply as standard. It's a fairly fairly specialist kind of requirement. Also has some significant safety implications. And then going below those temperatures, it is possible to work with helium cryostats and perform mechanical testing in cryostats and go all the way down to liquid helium temperatures. Again, highly specialized types of testing. Simultaneous control of temperature and ambient pressure and vacuum. Again, we don't supply vacuum chambers or vacuum furnace systems, but we have lots of experience of integrating vacuum chambers and vacuum furnace systems onto our equipment, and obviously that involves us providing the gripping solutions and providing the machine, providing gripping, integrating all of this, providing the strain measurement solutions for use inside those vacuum systems. So yeah, vacuum and inert gas, so backfilled with inert gas, that kind of thing, various temperatures, partial pressures of different gases, that kind of thing. All can be done. So temperature accuracy is basically comes down to the calibration accuracy of the thermocouples used. Typically, the chambers will use Type K thermocouples. These are checked in the factory prior to shipment. It is possible to recheck the calibrations in the field, so it's basically a temperature calibration. So that can be done, and so you have a calibrated temperature readout from the chamber. That's used in the control loop. So your chamber is going to give you an accurate temperature reading and control the temperature accurately. Final comment: how to minimize the time specimens are exposed to temperature prior to the test, whilst ensuring they're actually ready for testing. Yeah, I mean this is a question of what is the appropriate soak time for a particular specimen. And really, I think that's not a question that, as an equipment manufacturer, it's easy for us to answer, because this is going to be a function of the specimen. So it will depend on the thermal characteristics of the specimen rather than the equipment. So I'm just going to see if we have any other questions that have come through, and I'll pick those up. So, okay, let me run through here. So, okay. So there's a few points that we'll be getting back to individual customers on. I'm going to just go through the particular things that are more of general interest. How do you control specimen protect whilst ramping and soaking? Okay, so I mean, specimen protect will be the specimen protect feature in Blue Hill. This is the feature that will control the load that is applied to the specimen actively. Basically, if specimen protect is turned on while you are heating and ramping to temperature, that's a good thing generally, because it means that your specimen is not going to be subject to excessive loads caused by the expansion or contraction of the various load string components. So that's something that is perfect. Specimen protect is perfectly functional in those situations, and would be a useful thing to have. Okay, just looking here, I've got a question here. How do you control specimen protect? Well, okay, so I think we just answered that. Getting a prompt. Okay. Go to the next question. When using liquid nitrogen, do we need to use ventilation at the chamber's exhaust? Yes, yes, and I mean it's liquid nitrogen is an asphyxiant, and you definitely need to have adequate ventilation of the exhaust gases. Another question is, how uniform is the temperature inside the chamber? I don't have the exact numbers right in front of me, but typically we're looking at gradients throughout the volume of the chamber that would be something like 2 or 3 degrees centigrade. So pretty small, basically. I mean, you've got the air currents, you've got the fans that are circulating the air, and that is giving you very good uniformity. Okay.
We had one question on our custom mount, on our custom chamber mount for in between test frames. And yeah, so you would have a fixed, you would have something similar to this fixed on your test frame already. And then this is the removable part. And if you have a test chamber, you can roll it from your test frame onto these rails here. And then just very similar to what I showed you in the video. And then you can move the chamber onto the trolley to your next test frame, which needs to be the same height. And then you can roll your chamber onto that test frame without having to lift the chamber.
Great. Okay. So just see what else we have here.
Many questions coming in here.
Yeah, so I'm getting swamped here. It seems to be responding a little bit slowly. Right, okay. Sorry, everyone, this is...
Some people have asked for a recording or for the presentation itself, and yeah, we can email you the presentation, and yeah, we will have a recording uploaded on our YouTube channel where you can watch a recording of this webinar also.
Right, so we've had the temperature uniformity. Okay, if I have a tensile specimen in the chamber, is there a way to verify the temperature is uniform on the specimen? Yeah. Okay. So there it's a question of using thermocouples would be the typical way to do that. Take one or two or three thermocouples and place them on the specimen, shield them from the air. So they need to be sort of wrapped in some kind of tape, so they don't see the air temperature, they see the specimen temperature, and that they will give you the gradients on the specimen. Okay, I think we're nearly done.
Yeah, I think we'll follow up with the rest of these questions in email.
Yeah, I think that's probably the best thing. I think we are just about done.
All right. Yeah. Well, I can kind of wrap things up here. Thanks, Ian, Stephan, for addressing those. Again, yeah, for those that we didn't address live here, we will be sure to kind of review those after and follow up with those individuals by email. And yeah, again, like Stephan mentioned, I'll be making sure to send out an email with a copy of the recording along with the slide deck from today. So look for that probably at some point tomorrow. And I wanted to mention that we're already busy working on our next webinar topic, which we're planning on bringing to you at the end of, probably around the end of March. This one's going to be a follow-up to one of last year's most popular topics, which was the basics of Blue Hill Universal. So if you are a Blue Hill Universal user and just want to learn a little bit more about the software, I think it's going to be a really good session for you. Any new or infrequent users, or even people that are consider themselves to be more power users. There's usually some useful nuggets out of those sessions for everybody. So once we've opened registrations for that, you'll be the first group to hear about it. I'll share a registration link with you all. And with that said, I just want to thank Stephan for presenting today. Ian, thank you so much for keeping an eye on questions. And then thanks to all of you for attending. I know we went a little bit over today, so we appreciate you hanging out. Stay healthy, everyone. We hope to see you again next time.
Thank you, everyone. Bye-bye.
Yeah, bye.